Hello everyone and welcome to AISC's webinar, Direct Analysis Method, Applications and Examples, presented by David Landis. Today is December 8th, 2016. My name is Christina Harbour and I am with AISC's Continuing Education Group. I'll be moderating today's presentation. I want to introduce today's speaker. As Design Director for the Structures Group at Walter P. Moore, Dave Landis brings over 28 years of experience in structural engineering design. He's been involved in over 50 sports facility projects around the country and has also been engaged in a variety of other project types such as high-rise office towers, convention centers, parking garages, higher education facilities, and corporate campuses. He's a licensed engineer in Missouri and 17 other states. Dave earned his master's and bachelor's of science degrees in engineering at Auburn University. Welcome, Dave, and I'll let you take it from here.
Thank you, Christina, and good afternoon, everyone. My goal for today is to increase your understanding of the direct analysis method and how to apply it in your practice. Here's the outline for today's webinar. First, we'll review what the direct analysis method is and why we should use it. Then we'll compare the direct analysis method approach with the effective length method, look at how to apply the direct analysis method, and then go through some examples of applying the direct analysis method. Today's overview of the direct analysis method before we get into the examples is more just a refresher than a comprehensive introduction. The direct analysis method is a rational approach to stability analysis and design. It was introduced in a 2005 AISC specification as one of the acceptable methods for stability design. The features of the direct analysis method include P big delta and P little delta effects are accounted for directly through second order analysis. Geometric imperfections of the structure are accounted for through either direct inclusion in the analysis model or by applying notional loads to displace the structure. Inelastic effects, such as distributed plasticity, are accounted for in the analysis by using flexural and axial stiffness reductions. And the best part, then we design using K equals 1, no more K factors. The direct analysis method was first introduced into the 2005 specification in Appendix 7 as an alternate method for stability analysis and design. In the 2010 specification, the direct analysis method was moved to Chapter C and is now the primary method of stability analysis and design. The effective length method and first order analysis methods are still permitted as alternatives to the direct analysis method, but their use is limited and they have been moved back to Appendix 7. AISC Specification Chapter C outlines the direct analysis method approach and requirements. The commentary has a lot of additional information, so if you haven't thoroughly read the commentary yet, I recommend you do so. Also, AISC Design Guide 28, Stability Design of Steel Buildings, authored by Larry Griffith and Don White, is a good resource and covers stability design, second order effects, the direct analysis method, the effective length method, and the first order analysis method, and has some good examples for each. So if we've been using the effective length method, why should we now switch to the direct analysis method instead? First of all, it's now the primary method for stability analysis and design. It's applicable to all types of structural systems, such as moment frames, brace frames, and combined lateral systems. The direct analysis method captures the internal member forces more accurately. It results in the correct design of beams and connections, providing column rotational restraint and stability. And there's no need to calculate K factors. K is always equal to 1. The direct analysis method is applicable and accurate for all ranges of second order effects. And for frames with large second order effects, when the second order effect is greater than 1.5, the effective length method or the first order analysis method are no longer permitted, and the direct analysis method must be used instead. We'll be talking a lot today about second order effects, so first I want to start with the basics to make sure we're all on the same page regarding second order effects. Second order effects result from the displacement of the structural frame and also from the curvature of the individual members. Equilibrium must be satisfied on the deformed geometry of the structure. These include both system level effects and member level effects. The system level effects are the P big delta effects, and the member level effects are the P little delta effects. In other approximate stability design methods, the B1 and B2 factors account for these effects. In the direct analysis method, we model these secondary effects directly. First, let's look at P little delta effect. P little delta is the member level effect. Again, equilibrium must be satisfied on the deformed member geometry, and the member curvature produces additional moment in the member. Let's look at a simple example to demonstrate the P little delta effect, a simple beam with bending and axial load. If we apply a point load F at midspan of this simple beam, we get an initial deflection delta 1 caused by that point load and a midspan moment M equal to FL/4. Now, when we add an axial compressive load P to the member, we get additional deflection and additional moment caused by the axial load acting on the curved member geometry. The total midspan deflection is now delta, and the total moment becomes FL/4 plus P times delta. The P little delta component is the member level second order effect. Now let's look at the P big delta effect. This is an overall system level effect. Again, equilibrium must be satisfied on the deformed frame geometry. Let's look at a simple frame to demonstrate the P big delta effect, a brace frame stabilizing a single column. If we apply a horizontal load F to our brace frame, we get an initial deflection delta 1 caused by that horizontal load and a base overturning moment equal to F times the brace frame height H. Now, when we add a column load P to our stabilized system, we get additional lateral thrust, additional lateral frame deflection, and additional overturning moment caused by the column load P acting on that displaced frame geometry. So the total lateral displacement is now delta, and the total base overturning moment is now F times the frame height plus P times the total lateral displacement delta. This P big delta component is the system level second order effect caused by the displacement of the frame. Now let's look at both P big delta and P little delta together. We'll look at a simple cantilevered column with vertical and lateral loads applied at the top of the column and investigate the resulting moment diagram. The triangular moment diagram at the far right represents the first order moment, the lateral load H times the column height L. The next moment diagram to the left, the smaller triangle, represents the P big delta portion of the second order effects, the vertical load P times the column displacement delta. The third moment diagram, the thin curve portion, represents the P little delta portion of the second order effects, the effect of the axial load acting on the curved shape of the column. The total moment diagram is the sum of each of those components, the first order moments plus both the P big delta and P little delta second order moments. By applying the moment area method of calculating deflection, we can see that both the P big delta and P little delta secondary moments contribute to the overall system deflection. The other important thing to recognize about second order effects is that they're not linear. So when we're analyzing a structure and including second order effects, it's not appropriate to superimpose different load cases by just adding the results of independently run cases. The structure should be analyzed with all the loads applied in a single nonlinear analysis case. Before we get into the application of the direct analysis method, I'd like to spend a few minutes comparing the direct analysis method with the effective length method. Both methods can employ either a second order or amplified first order analysis. By amplified first order, I mean conducting a first order analysis and then using the B1 and B2 amplification factors in Appendix 8 to approximate the second order effects. B1 for the P little delta effects and B2 for the P big delta effects. In today's discussion, though, I'll just be focusing on using the second order analysis approach. Second order analysis is available in most of the commercial structural software, and in my mind is the appropriate approach to use. For member stiffness, the effective length method uses the nominal member stiffness. The direct analysis method uses reduced member stiffness in the strength analysis to account for softening of the lateral system due to residual stresses and distributed plasticity. Notional loads. This may come as a surprise to some of you, but when the 2010 specification came out, the effective length method now requires the use of notional loads. When using the effective length method, notional loads of at least 0.002 times the gravity loads must be applied in combination with the gravity loads. In the effective length method, these notional loads do not need to be additive to other lateral loads. They're minimums. The case of the gravity loads combined with the notional loads will probably only control for structures with very high gravity loads and low lateral loads. The direct analysis method requires explicit consideration of initial frame geometry imperfections. This is most commonly done by applying notional lateral loads to displace the structure. Notional loads can be applied as a minimum lateral load acting concurrently with gravity loads for structures with second order effects less than 1.7. If If the second order effects are greater than 1.7, then the notional loads must be additive to the lateral loads and acting in the same direction as the lateral loads. Column effective length. For the effective length method, K-factors must be used for sway frames. Later on, I'll point out some of the difficulties in determining the correct K-factors. A nice benefit of using the direct analysis method is that K is always equal to 1 in the direct analysis method. No more K-factors to worry about, even for sway frames. Limitations. The effective length method is limited to second order effects less than 1.5. If you have a flexible moment frame, for example, and the second order effects are greater than 1.5, then you'll not be permitted to use the effective length method and will be required to use the direct analysis method instead. The direct analysis method is not limited in its use. It can be used for any type of structure and for any magnitude of second order effects. And last line, if the effective length method is now in AISC specification Appendix 7 as an alternative method of design, while the direct analysis method is found in Chapter C and is the primary method for stability analysis and design. Even though the direct analysis method is now the primary method in Chapter C, the effective length method and first order method are still permitted to be used if the second order effects are less than 1.5. Another way to look at the differences in approach between the direct analysis method and the effective length method is to compare the demand and capacity curves. Here we have an example of beam column axial force and moment interaction checks using the effective length method on the left and the direct analysis method on the right. A few things to note in these graphs. Let's look at the effective length method on the left. The thinner curved line of the graph represents the actual response of the beam column element as the load is applied and increased. The heavier curved line represents our effective length method analysis. Note that the effective length method analysis underpredicts the actual moment at the strength limit state. The lower sloping line is the strength check. The lower sloping line for the strength check represents the member strength interaction curve using P nominal based on an effective column length of K times L. So the column capacity for a strength check is based on a reduced compression capacity for a longer column length. Now let's look at the direct analysis method for the same beam column. Once again, the thinner curved line represents the actual response of the beam column as the load is applied and increased. The heavier curved line represents our direct analysis method with the softened structural stiffness. Note that at the strength limit state, the analysis moment now much more closely predicts the actual moment at the limit state. The lower sloping line here represents the strength check for the member strength interaction curve using P nominal based on the actual column length L without any K factor. So now instead of the strength check being based on a reduced compression capacity, the beam column is checked for the increased moment demand due to the more flexible structure. Note that this increased moment demand associated with the softened, more flexible structure used in the direct analysis method much more closely represents the actual loads in the structure at the strength limit state. Now we'll look at a comparison of the direct analysis method versus the effective length method using a very simple example, a single cantilevered column with a fixed base and an axial load applied at the top. The column in the upper right represents our effective length model. I'm using the older pre-2010 effective length method here without the application of a notional load to illustrate the difference between the two methods. So for the effective length method, we're just applying an axial load P at the top. For the direct analysis method, we'll look at the column at the left. In addition to the axial load P, we apply a notional lateral load of 0.002 P and reduce the column flexural stiffness. Now let's look at the axial load in the moment graph. We'll start by applying our load and track our analysis on the graph as the load progresses. Starting with the old effective length method approach, we apply 150 kips axial load to the column. In our analysis, we now have P equals 150 kips and 0 moment. Now we'll increase the column load to 250 kips. In our effective length method analysis, we now have P equals 250 kips and still have no moment. Now we'll increase the column load to the 275 kip column strength capacity. In our effective length method analysis, we now have P equals 275 kips and still have no moment. The lower sloping line here is the strength interaction curve for this column using the effective length method. This is the strength interaction curve based on an effective length using k equals 2 for the cantilevered column condition. Now let's look at the same column again, but this time using the direct analysis method. For the direct analysis method, we'll reduce the column stiffness, apply a notional lateral load of 0.002p, and run a second order analysis. Once again, we'll apply a load of 150 kips axial load to the column, but now we also apply an associated notional lateral load of 0.002 times 150 kips equals 0.3 kips, and run our second order analysis. Notice that we now have moment in our column that didn't show up in the effective length method. Now we increase the column load to 250 kips and increase the notional lateral load to 0.5 kips and rerun our second order analysis. Now our column has substantial moment that didn't show up in the effective length method analysis. Also notice the nonlinearity of the response resulting from the second order effects. Now we'll increase both the axial load and associated notional load up to the column capacity. Notice a large base moment that results that was not captured in the effective length method. Also notice a different strength interaction curve for the direct analysis method. This higher sloping line is the strength interaction curve for the column using the direct analysis method. This is the column strength interaction curve based on effective column length equal to the actual column length with k equals 1. In this particular example, the column axial load capacity is almost the same, just slightly less than we had calculated using the effective length method, even though the effective length method had no moment, but the direct analysis method had a large moment. This example was intentionally extreme in order to point out an important difference between the two methods. The effective length method approach will miss some of the moments in the system. For this example, what moment would you have designed the column base plate for if you had used the effective length method? The direct analysis method accurately captures the moments that occur in the structure at the limit state. When using the effective length method, the moments necessary to stabilize the frame at the strength limit state will be underestimated. When using the direct analysis method, the beams and connections providing stability to your frame will be designed for the appropriate moments needed to stabilize the frame at the strength limit state. Due to the higher nonlinearity of the direct analysis method, you also need to be aware of the potential sensitivity of the demand capacity ratios if you have a very flexible structure. Notice in our cantilevered column example how the DCRs were linear for the effective length method approach, shown here in blue, but can quickly change with small increments of load when using the direct analysis method, shown here in red, especially as the limit state is approached. In this example, our last small load increment for the direct analysis method resulted in a large increase in the DCR. Looking at this another way, here's a graph of the interaction value for each method as the column axial load increases. The older effective length method was linear, while the direct analysis method can be highly nonlinear, especially with flexible structures as the strength limit state is approached. So, when using the direct analysis method, it's important to rerun your analysis if loads increase or if member sizes are reduced. In the previous cantilevered column example, I used the older pre-2010 effective length method without notional loads to highlight the difference between the two methods. The current effective length method does require the application of notional loads as a minimum lateral load to be applied in combination with the gravity loads. However, even with the application of lateral loads, the effective length method still underpredicts the moments, similar to the previous example, as can be seen here in this graph. Again, the direct analysis method approach comes much closer to the actual structural behavior and will result in higher design moments than the effective length method. This is because we soften the frame stiffness when using the direct analysis method. Here's a brief summary of the steps for applying the direct analysis method. We'll get into the specifics of each of these steps and then we'll look at some examples. First, we need to accurately model the frame behavior. We need to factor all loads, even for ASD. We need to consider initial frame imperfections, usually by the application of notional loads. We need to reduce all stiffness that contributes to stability of the system. Then we need to conduct a second order analysis that captures both the P big delta and P little delta effects. And then we use k equals 1 for all member design. When doing serviceability checks, though, we will use the nominal frame stiffness instead of the reduced stiffness. Now we'll go through the specifics of each of these steps, starting with accurately modeling frame behavior. It's important we accurately model the structural system in order to accurately capture the true behavior. This includes correct model geometry, correct member sizes and orientations, correct boundary conditions that accurately reflect actual conditions, correct member properties and stiffnesses, and correct and complete loads, including the effects of leaning columns. All this seems pretty basic, but it's important that the model accurately represent the structural behavior. I mentioned leaning columns. By leaning columns, I mean gravity columns that support gravity loads but are not part of the lateral load resisting system. There are gravity columns that lean on the lateral system for stability. This is something I see missed a lot when someone is analyzing a frame with an isolated 2D model as shown here. They often forget to add the effect from all the gravity columns that rely on that frame for support and work to destabilize the frame. The columns on the right here are what I've referred to as the leaning columns. They're the columns that represent all the other gravity columns that are stabilized by the frame we're analyzing. As the frame deflects, these columns lean on the lateral system for support, and these gravity columns deflect also and add to the overall P big delta effect. The P big delta effect from these leaning columns works to destabilize the frame, so they must be included in our analysis. All loads or conditions that work to destabilize the structural system should be accurately included in the structural model. The die-hard ASD folks out there won't like this one, but you need to factor all your loads, even for allowable strength design. So why do you need to factor loads for ASD? Well, we're trying to capture the actual structural behavior at the strength limit state. Going back to our previously cantilevered column example, you can see how nonlinear the structural behavior can be due to second-order effects as we approach the strength limit state. So even when using allowable strength design, we must factor our loads up to the factored strength limit state level. If you're using LRFD, the standard LRFD load factors are applied. For instance, 1.4 dead or 1.2 dead plus 1.6 live. If you're using ASD, you'll need to factor all your loads up by 1.6, run your second order analysis, and then divide your resulting member forces by 1.6. Again, this is to accurately capture the structural behavior at the strength limit state. Just one more reason to switch to LRFD if you haven't already done so. Again, include all the loads that affect stability, including leaning columns and all other destabilizing loads or effect. Next step, consider initial frame imperfections, usually by the application of notional loads. We all know buildings aren't built perfect. Initial imperfections, such as out of straightness and out of plumbness, result from fabrication and erection tolerances and create destabilizing effects that work to destabilize the structure. Member out of straightness contributes to P little delta effects in the members. Story out of plumbness contributes to the P big delta effects in the overall frame. Only the initial member out of straightness is included in the column strength curves. In the direct analysis method, the story out of plumbness needs to be accounted for in our analysis model. This can be done either by modeling an out of plumb story geometry or by applying notional lateral loads to laterally deflect the structure. We apply notional loads to displace the structure laterally to induce an initial out of plumbness. These notional loads need to be applied at each level of the structure based on the distribution of the gravity loads. The specification defines notional lateral loads equal to 0.002 times the gravity loads applied at that level. For instance, in the frame shown here, the notional lateral load to be applied at level 2 is equal to 0.002 times the gravity loads applied at level 2. The notional load applied to level 3 is 0.002 times the gravity loads applied at level 3, and so on. The notional lateral load should be applied simultaneously with the gravity loads at each level in the direction that most destabilizes the structure. For instance, for the frame shown here, one case with all notional loads acting to the right, and another case with all notional loads acting to the left. The 0.002 factor is consistent with the Code of Standard Practice tolerance of H over 500 for column or out-of-story plumbness. If you specify tighter out-of-plumbness tolerance and are sure that the tighter tolerances will be achieved, you could reduce the 0.002 factor accordingly to the tighter tolerance. Likewise, if you allow relaxed tolerances, or perhaps if you need to check an out-of-tolerance condition, then you should use a higher factor based on the larger out-of-plumbness condition. You do have the option of modeling the out-of-plumb geometry instead of applying notional lateral loads. However, it's often easier to apply the notional loads in each direction than it is to provide different starting geometry for each direction, so usually people apply the notional loads. A few nuances on the application of the notional loads. The specification defines the notional loads as 0.002 times alpha times y sub I, where alpha is defined as 1.0 for LRFD and 1.6 for ASD, and y sub I is the gravity load applied at level I. The intent here is that the notional loads are factored loads. So alpha is 1.0 for LRFD with the assumption that the notional loads are factored the same as the gravity loads. Alpha is 1.6 for ASD to bring them up to the factored level. Also, the notional lateral loads need to be added to other lateral loads and applied in the same direction as the other lateral loads. For instance, when we're doing wind loads applied to this frame acting to the right, then we need to apply the notional loads acting to the right at the same time. Then when we apply the wind load acting to the left, we need to apply the notional loads acting to the left also. We always need to apply the notional loads in the direction that provides the greatest destabilizing effect. Specification does have an exception though. If the second order effects are low enough, less than 1.7 using the reduced frame stiffness, or less than 1.5 using the nominal unreduced stiffness, then you're permitted to apply the notional loads only with the gravity-only combinations, and need not apply the notional loads as additive to other lateral loads. The reason for this is that if the second order effects are low enough, then not adding the notional loads along with the other lateral loads results in errors that are within reason, and the approach is not any more inaccurate than other methods. The 2005 specification used a 1.5 limit based on unreduced frame stiffness. The 2010 specification now has a 1.7 limit, but that is based on the reduced frame stiffness instead of the unreduced stiffness. In the 2010 commentary, either limit can be used, 1.5 for the nominal unreduced stiffness or 1.7 for the reduced stiffness. The second order to first order ratio should be checked using a load combination that includes the heaviest factored gravity loads in combination with some lateral load. The lateral load can be notional loads or other lateral loads. The important part is that you're using the heaviest gravity loads. Of course, a simplification is to apply the notional lateral loads to all load combinations, and then you don't need to check the second order to first order drift ratios. Some software packages can automate the application of notional loads. This is an example from SAP 2000, one of the programs I often use. Here I'm creating a notional lateral load pattern for dead load acting in the y direction called n dead y and defining it as an auto-generated notional load. I'll be using SAP for the examples today, but other programs also can be used to automate the direct analysis method. Each program works a little bit differently, so you'll need to get familiar with how your software works. Now you can see in the left column, I've defined load patterns dead, live, wind x, and wind y, and notional load patterns for n dead x, n dead y, n live x, and n live y. At the bottom window, I'm defining the n live y notional load to be based on the live load pattern times 0.002 applied in the y direction. The notional loads will then be used in load combinations with the same load factors that are applied to the associated gravity loads. For instance, 1.2 n dead y plus 1.6 n live y will be combined with 1.2 dead plus 1.6 live. Next, we'll need to reduce all stiffness that contributes to stability. Residual stresses result from the rolling process. These residual stresses result in some portions of the section yielding before other sections. For instance, for the wide flange column shown here, the tips of the flanges of a compression member will yield before the web. This impacts the column flexural strength and buckling resistance, and also the stiffness of the system. So to account for the effects of residual stresses and distributed plasticity, we reduce the stiffness of all members that contribute to stability. For axial stiffness, we use 0.8 EA. For flexural stiffness, we use 0.8 tau B EI, where tau B is less than or equal to 1 depending on the magnitude of the axial load. For low axial loads, when the required axial strength is less than half the yield load, then tau B equals 1 and the flexural stiffness reduces to 0.8 EI. For higher axial loads, tau B is less than 1 and is calculated based on the ratio of the required axial strength to the yield strength, and the resulting flexural stiffness becomes less than 0.8 EI. Since tau B is 1 when the axial load is less than 0.5 PY, tau B is often 1 for moment frames. The specification offers a simplification for tau B that allows you to increase the notional lateral loads by an additional 0.001 times the gravity loads, so 0.003 times the gravity load instead of 0.002, and then tau B can be equal to 1 instead of having to calculate tau B. The stiffness reduction can be automated in some software packages as well. Here's an example again from SAP 2000. You can see in the red box I have selected LRFD design, the direct analysis method, second order analysis method, and the tau B variable stiffness reduction option. This means that SAP will calculate tau B for each member based on the axial load demand. There are also options for tau B fixed or for no modification. If you select the tau B fixed method, you'll need to go back and modify your notional load definitions to use the 0.003 times the gravity loads instead of 0.002 times the gravity loads. If you select no modification, then SAP will use the nominal unreduced member stiffness, so this would be for serviceability checks. You will need to know how your software package applies the stiffness reductions. For instance, SAP will not reduce the stiffness until after the member design checks have been performed. So you'll need to run the analysis, perform a design check of the members, then rerun the analysis so SAP can calculate the proper stiffness reductions, and then redo the design check again. Then if you change member sizes, you'll need to redo that cycle of running the analysis, performing a design check, then rerunning the analysis so SAP can calculate the correct stiffness reductions, and then perform the final design check again. Next step, perform a second order analysis that includes both P big delta and P little delta effects. Our second order analysis needs to capture both the P big delta effects and the P little delta effects. Remember, P big delta is the overall system effect, the effect of loads acting on the displaced location of the joints. And P little delta is the effect of axial loads acting on the deflected shapes of the individual members between joints. As I mentioned earlier, both P big delta and P little delta contribute to the overall system deflections, and therefore both are important to the stability of the structure and both need to be included in the analysis. You'll need to know how your software addresses P big delta and P little delta. For many software packages, you'll need to mesh the compression elements into smaller segments in order to accurately capture the true P little delta effects. The number of segments you need to mesh these members into depends on several factors, including how your software handles P delta and the magnitude of the secondary effects. I like to mesh the compression elements into 4 segments. That way there are nodes at member midspans and at member quarter points as shown here, and secondary effects for both single curvature and double curvature can usually be very accurate. Notice that I did not mesh the beams here. If there's not much compression in the beams, such as in a moment frame like this, then there's no need to mesh them since there will not be a significant P little delta effect with those beams. However, if you have some collector beams with high compression forces, then you should mesh those as well. Some software packages enable you to automate meshing of the frame elements. Here's an example again from SAP 2000. I select the frame members I want to mesh, then select auto meshing and tell it to mesh the elements. In this case, I selected 4 segments for the meshing. Next, you'll need to generate nonlinear load cases. Remember, the second order analysis is nonlinear, so running separate load cases individually and then combining the individually run cases in linear combinations is not appropriate. You'll need to run a series of nonlinear cases that include all the gravity loads, notional loads, and lateral loads combined into a single nonlinear case. In this example from SAP 2000, I'm converting previously defined load combinations into individual nonlinear cases for the second order analysis. Now run a second order elastic analysis that includes both P big delta and P little delta. Make sure you know how your software handles the second order analysis and the stiffness reductions. For instance, in SAP 2000, the reduction factors to EI and EA are assigned only after the design check is run. Iterate as necessary. If you change member sizes or loads, you'll need to redo the cycle of running the analysis, performing a design check, then rerunning the analysis so SAP can calculate the correct stiffness reductions, and then to perform the design check again. After the members are sized, check the second order to first order drift ratios for each level. If the second order to first order drift ratio is less than 1.7, using the reduced stiffness, or 1.5 using the nominal stiffness, then the notional loads are not required to be included with other lateral load combinations. The notional lateral loads are only required in the gravity load combinations. However, if the second order effects are greater than 1.7, using the reduced stiffness, or 1.5 using the nominal stiffness, then the notional loads are required to be included in all load combinations, including those with other lateral loads. A simplification to avoid this check is to use the notional lateral loads in all the load combinations. Next step, K equals 1 for all member design. In all the design equations that have a K factor, K equals 1, and KL is just equal to L, which means that the effective length is always equal to the actual member length. No more K factor, which is good because K factors are often applied incorrectly. I'll show an example later in which the k-factors are often incorrect. So why are we able to eliminate the k-factor in the direct analysis method? Well, the direct analysis method accounts for both the p big delta and p little delta effects. Geometric imperfections are considered explicitly, and the loss of stiffness under high compression loads is considered in the analysis by reducing the member stiffness. The result is that the direct analysis method forces are very close to the actual response of the structure at the strength limit state. If you're using AS allowable strength design, you'll need to divide the analysis forces by 1.6, since they were factored up by 1.6 for the analysis. And remember, since the analysis is nonlinear, if any member sizes change or loads change, then you'll need to rerun the analysis and recheck the designs. And last point for the direct analysis method, serviceability checks are done using the unreduced stiffness. The reduced stiffness is only used for the strength analysis. Use the nominal unreduced stiffness for all serviceability checks. So use the nominal unreduced stiffness when checking deflections or wind or seismic drifts, when determining building periods and mode shapes, and for vibration checks. The reduced stiffness properties are only used for the strength analysis. Okay, to summarize the direct analysis method, accurately model frame behavior, including all loads and conditions that destabilize the structure. Factor loads for the analysis, even for ASD. Consider initial imperfections, usually by the application of notional lateral loads. Reduce all stiffness that contributes to stability. Perform a second-order analysis that includes both P big delta and P little delta effects. Mesh the compression members in order to capture the P little delta effects. K equals 1 in all member design equations. And last, check serviceability using the nominal unreduced stiffness properties. Okay, Christina, time for our first polling question.
All right, let's take a break to test your understanding of the first part of the presentation. The question is, true or false, tau sub b calculations can be simplified by increasing notional lateral loads from 0.002 alpha y sub I to 0.003 alpha y sub I. It's a true or false question. Go ahead and select your question right there on the screen and hit submit. Read it again. True or false, tau sub b calculations can be simplified by increasing notional lateral loads from 0.002 alpha y sub I to 0.003 alpha y sub I. True or false? Okay, it looks like most of our participants have responded. Skip to the results. And it looks like about 86% of our participants answered that true. Dave?
And that's correct. True. Tau b calculations can be simplified to tau b equals 1 by using the notional lateral loads of 0.003 alpha y sub I instead of 0.002. So most of us got it right. Let's see, do I have control again?
Yes. You should be able to advance.
There we go. Okay, now we'll take a look at some examples using the direct analysis method. For our first example, we'll look at simple 2D frame supporting a grain storage bin. This is a two-level frame with the upper portion consisting of a brace frame and the lower portion being a moment frame with pin-based columns. We'll check the columns for strength using LRFD and the direct analysis method. The loads are shown here. The grain load is a vertical load PG equals 60 kips at the top of each column. Dead load PD is a vertical load of 5 kips at the top of each column. The wind load is a total of 7 kips with a centroid acting 9 feet above the top of the frame, resulting in a horizontal WH equals 3.5 at the top of each column, and a vertical force couple WV equals plus or minus 5¼ kips at the top of each column, acting either up or down. We use A992 steel for the wide flange shapes and A36 steel rods for the braces. We'll use a delta over H equals 0.002 for the initial out of plumbness, which means we'll apply notional lateral loads equals to 0.002 times the gravity loads. And we don't have any inner story drift limits. All columns are oriented strong axis bending in the plane shown, and columns are braced out of plane at each joint. All lateral load resistance in the upper tier is provided by the tension-only rod bracing, and all lateral load resistance in the lower tier is provided by the flexural resistance of the columns. Tension rods have pin connections, and the horizontal beams have both the double angle shear connections that we modeled as pins. We'll use the following load combinations. Combination 1 consists of gravity loads and the associated notional lateral loads, so we have 1.4 times the quantity dead plus grain, plus 1.4 times the quantity notional dead plus notional grain. We've treated the grain load here as a dead load. Note that the notional loads use the same load factor as the associated gravity loads in the combination. Combination 2 is the same as combination 1, except that the notional lateral loads are acting in the opposite direction. Combinations 3 through 6 are gravity and wind combinations. Note that we did not include any notional loads in these combinations. We've assumed here that the second order effects are low and that will not be required to apply the notional lateral loads at the same time as the wind loads. We'll have to check this assumption later. If the second order effects are large, then we'll also be required to apply the notional lateral loads with the wind loads, acting in the same direction as the wind loads. Due to symmetry, combinations 1 and 2 and combinations 3 and 4 will produce the same results, so we'll only need to look at combinations 1 and 3. Also, by inspection, combinations 5 and 6 will not control. Now run a second order analysis and compare second order results with first order results. The maximum second order to first order ratio here is 1.2 with nominal unreduced stiffness properties, which is less than 1.5, so notional loads are not required to be added to lateral loads, and our previous assumption was correct. Now we'll apply the stiffness reduction to our second order strength analysis. The axial stiffness is reduced to 0.8 EA. The flexural stiffness is reduced to 0.8 tau B EI. We're able to use tau B equals 1.0 in this case, since PR over PY for all columns is less than 0.5. So we'll mesh the column elements, reduce the stiffness of all members using 0.8 EA and 0.8 EI, and run a second order analysis. We ran a second order analysis to capture both the P big delta and P little delta effects with reduced stiffness. The results are tabulated here. I won't go through all the numbers, but I want to point out the process on the right. First, we'll use K equals 1 for all members in the strength calculation equations. We used reduced stiffnesses of 0.8 EA and 0.8 EI for the second order analysis, but we use the full nominal properties in all the capacity equations. Then we check interaction using the standard interaction equations in Chapter H. We'll go through one of the column calculations on the next slide. In this case, all the members are okay for strength, with the highest interaction ratio of 0.89 for load combinations 3 and 4. Here are the calculations for column C1. Again, for the capacity calculations, we use the nominal member properties as you normally would, without any reduction. First, we'll determine the compression capacity like we normally would, but with K equals 1. K equals 1, so KL equals Ly equals 14 feet. Ly over Ry equals 108. The elastic buckling stress, Fe, equals 24.4 KSI. The critical compression stress, Phi F critical, equals 19.1 KSI. The nominal compression capacity, Phi Pn, equals 19.1 KSI times 11.2 square inches, equals 213 kips. And now we calculate the column moment capacity just like we normally would. C sub B equals 1.67, since we have a linear moment diagram with zero moment at one end. The end brace length equals 14 feet, and Phi Mn is 231 kip feet. Now we'll use the Chapter H interaction equations to check demand versus capacity. Pu equals 112.9 kips, and Mu equals 94.7 kip feet. Pu over Phi Pn equals 0.53, which is greater than 0.2, so we'll use interaction equation H1-1a. The interaction equation results in a DCR of 0.89, which is less than 1, so our strength check is okay. For the second example, we'll look at an unsymmetrical one-story moment frame with leaning columns. You can see the moment frame geometry here. Note the leaning column on the right. This represents all the gravity columns that lean on this moment frame for stability. The 1,875 kips is the sum of the gravity load from all those gravity columns that this frame is stabilizing. It's important that this load is captured in our analysis, since that load works to destabilize the moment frame. We'll use LRFD in the direct analysis method to evaluate the frame for strength. All column loads shown here are factored gravity loads. All columns are subjected to strong axis bending in the plane shown. The wind load is 12 kips from ASC 705 unfactored. The finite element model is shown here. The column bases have rotational springs, and the columns are moment connected at the top, except for the leaner column at the right that represents all the gravity columns. The linear column is pinned at both top and bottom. We'll assume all column bases have a rotational spring stiffness beta equals 6 EI over 10L. Inner story drift will be limited to H over 500 for the full wind load, and we'll use A992 steel. Here's our model. The loads are listed in the left table, and the base spring stiffnesses are listed in the right table. Note that the columns are meshed into 4 segments each to capture the P little delta Fx. The notional lateral loads will be 0.002 y sub I. So we need to perform a second order elastic analysis that captures both P big delta and P little delta effects using reduced member stiffness. The notional lateral loads are 0.002 times the gravity loads. We'll apply property modifiers for the second order analysis with an axial stiffness of 0.8 EA and flexural stiffness of 0.8 tau B EI. We're going to assume tau B equals 1 for our first iteration, and then we'll check that assumption later. Here are the load combinations based on ASC 7 LRFD combinations with the notional lateral loads added. As before, note that the load factors for the notional lateral loads correspond to the load factors for the gravity loads. This time, in combinations 4A and 4B, we're also combining the notional loads with the wind loads. Note that the notional loads are applied in the same direction as the wind loads. We run the second order analysis using the reduced stiffness properties and compare the second order to first order ratio. For this case, the second order effects are greater than 1.7. Therefore, the notional loads are required to be added additively to the lateral loads in all load combinations, not just the gravity load combinations as we had done in the previous example. Here are the results for some of the load combinations from the second order analysis. Now we'll check to see whether or not our assumption that tau B equals 1 is valid or not. We'll check the column with the highest axial force, column C3. PR equals 272 kips, and the column area equals 17 square inches. PY equals 50 KSI times 17 square inches equals 850 kips. PR over PY equals 0.32, which is less than 0.5, so therefore it's confirmed that tau B equals 1. This needs to be evaluated for each of the compression members. In this example, tau B is 1 for all the columns, and this is often the case for moment frames. Next, we check the member designs. K equals 1 for all members in the strength calculations, and the strength calculations are done using the nominal section properties. We'll go through the design check calculations for column C3. The size in our analysis was a W12 by 58. The governing load combination is 4A, with PR equals 228 kips compression, and MR equals 1,374 kip inches. K equals 1, KL equals L equals 180 inches. KL over RY equals 71.7, which is less than 4.71 times the square root of E over Fy, so equation 3.2 applies for column compression capacity. The elastic buckling stress equals 55.65 KSI using K equals 1, and the critical compression stress FCR equals 34.33 KSI, so phi PN equals 525 kips. Now we'll look at the column moment capacity. For the W12 by 58 column, the unbraced length LB is 15 feet. MR at the top is negative 1,374 kip inches, and MR at the bottom is positive 431 kip inches with the column in reverse curvature. We'll calculate C sub B using C sub B equation F11 and find C sub B equals to 2.11. Calculate phi MN using equation F22 and C sub B equals 2.11, and we find that phi MN equals 3,888 kip inches. And finally, we check the interaction equation H1-1A, and we find we have a DCR of 0.75, which is less than 1, so the W12 by 58 column size is okay. Okay, here's an example for the ASD fans out there. For example 3, we'll analyze a moment frame using ASD and the direct analysis method. The frame geometry, initial member sizes, and loads are shown here. The frames are single bay frames spaced at 35 foot on center. The columns are braced out of plane at the roof level. We're using A992 steel. Wind pressure equals 20 PSF using ASC 705. Gravity load equals 20 PSF dead plus 60 PSF live equals 80 PSF total. We'll use an initial out of plumbness delta over H equals 0.002, which means our notional lateral loads will be 0.002 times the gravity loads. And we'll limit lateral load deflection to 1 inch under wind and total gravity load using second order analysis. All lateral load resistance is provided by the moment connection between the left-hand column and the roof beam. We're assuming a rigid moment connection. The right-hand beam to column connection is a simple shear connection, which we're assuming to be pinned. The dead, live, and wind loads are shown here. The notional lateral loads, Ni, equals 0.002 alpha y sub I, with alpha equals 1.6 for ASD. Notional dead load N dead equals 0.002 times alpha times the dead loads equals 0.0654 times alpha kips. Notional live load N live, 0.002 times alpha times the live load equals 0.168 times alpha kips. I left alpha as a variable here in the notional loads because I'll factor the notional loads later at the same time that I factor the rest of the loads. Now we'll apply the ASD load combinations. Remember that for ASD, due to the nonlinear second order behavior, member forces are obtained by analyzing the structure for 1.6 times the ASD load combinations, then dividing those results by 1.6. The load combinations are shown here. Note that all the typical ASD combinations are factored by 1.6. In combinations 1A through 3B, we're combining the notional loads with the gravity loads. The other combinations are 1.6 times the ASD combinations with wind without the notional loads. We're making the assumption here again that the second order effects are low enough that the notional loads do not need to be applied with the wind loads. We'll need to check that assumption later. Direct analysis is performed using the reduced properties at 1.6 times the ASD load combination level, using second order analysis that considers both the P big delta and P little delta effects. Column elements are meshed to capture the P little delta effects. Now we check the lateral drift ratio for the application of notional lateral loads, this time using the unreduced nominal stiffness. The second order over first order drift ratio is less than 1.5. Therefore, it's permissible to apply the notional lateral loads only in the gravity-only combinations, so our previous load combinations without adding the notional loads to the wind loads are okay. Section properties are reduced for the second order strength analysis. Axial stiffness equals 0.8 EA. Flexural stiffness equals 0.8 tau B EI. Once again, we're going to assume tau B equals 1 to start with, and then we'll check this assumption after we run the analysis. We run the second order analysis and check drift. The second order drift is way over the desired limit, so the frame must be stiffened. Note that the drift check is performed using the nominal unreduced stiffness. A W36 by 150 beam and a W18 by 97 column are required to meet the drift limits. After increasing member sizes, we reduce the stiffness properties to 0.8 EA and 0.8 EI and rerun the second order strength analysis. The results of the ASD load combinations are tabulated here after dividing the analysis results by 1.6. Remember that we multiplied all ASD loads by 1.6 to factor them up to the strength limit state, so we divide the analysis results by 1.6 in our ASD calcs. At the bottom of the slide, we check alpha times PR versus 0.5 P yield to see if tau B is equal to 1. In this case, we were drift controlled, and alpha PR is much less than 0.5 P yield, so our assumption was right, and tau B is equal to 1. K equals 1 in the strength calculations for all members, and strength calculations performed using the nominal section properties. The strength calculations aren't going to be shown here, but since the frame was drift controlled, the increased member sizes easily worked. Okay, Christina, time for our next polling question.
All right, here's another opportunity for everyone to test their understanding. Here's the question. In the direct analysis method, when are reduced stiffness properties used? Is it A, strength analysis, B, member capacity calculations, C, serviceability checks, D, all of the above, or E, both A and B? In the direct analysis method, when are reduced stiffness properties used? A, strength analysis, B, member capacity calculations, C, serviceability checks, D, all of the above, or E, both A and B? Okay, it looks like most of our participants have responded. Let's skip to the results. Well, Dave, it looks like the majority of our participants said E, both A and B.
Yeah, this question was a little tricky on purpose here. And the correct answer is A, strength analysis. So in the direct analysis method, we only reduce the stiffness properties for the strength analysis. So the lateral analysis, where we're going to get our moments and axial loads for strength checks, we use reduced properties. When we're actually checking serviceability, we use the full nominal properties. And when we're doing the strength calculations, the checks on using the member areas and member moments of inertia, we're going to use the full properties of the section. So we only reduce it for the strength lateral analysis. Okay, for example 4, we'll look at a 10-story building with brace frames in one direction and moment frames in the other direction. The plan layout is as shown on the left. We have 2 moment frames in the east-west direction at the south face and at the north face. The moment frame elevation is shown here in the center. Then we have 2 brace frames near the center of the building, located at the center. The brace frame elevation is shown here on the right. Note that we have a large number of leaning columns in each direction. These are gravity columns that aren't participating in the lateral system. We'll use LRFD in the direct analysis method to evaluate the moment frame and brace frame, and we'll also look at the moment frame using the effective length method for comparison. We built the full 3D model, including all floors and roof, the brace frames, the moment frames, and including all gravity columns as well. We included all gravity loads and wind and seismic loads in each direction. Note that if we had only used 2D models for each direction, we would need to add dummy columns to represent all the gravity columns leaning on the frames for stability. Here are the gravity loads. The floor uses a 3-inch composite steel deck plus 3.5-inch lightweight slab equals 50 psf. Superimposed dead load plus floor framing allowance is 15 psf. We have a wall load of 25 psf over the entire floor area, and a reducible live load of 100 psf. For the roof, we'll same the same dead load as the floors, but we'll have a live load of 30 psf unreducible. We'll reduce floor live load separately for the floor framing and for the columns using the IBC live load reduction equations. For the moment frame beams, the 100 psf live load reduces to 75 psf. We can reduce the live load further for the columns since the columns have a larger tributary area. The way we handled that in this model is to apply the reduced floor live load as a uniform load to each floor, and then apply compensating upward point live loads at the column nodes so that the net column live load is correct for the column tributary area. That process is shown here in the spreadsheet with the compensating upward column load for each floor shown in the far right column. Next, we use a column load takedown spreadsheet to determine preliminary sizes for each column. We'll use these as sizes as starting column sizes for our analysis model. For wind loads, we're using ASC 705 and a basic wind speed of 90 miles per hour. I won't go through the wind calcs in this example. We'll use the auto-generated wind loads in SAP. For seismic loads, we're using ASC 705 and the seismic parameters shown here. We'll use steel systems not specifically detailed for seismic resistance with R equals 3. Here's the period information for seismic design. I won't go through the seismic load generation. We'll use the seismic load auto generation in SAP. What I do want to point out here is that we need to calculate the building periods and mode shapes using the nominal properties, not the reduced properties. If you use the reduced properties, if you're not limited by the code upper limit on period, then your building period would be too long and you'd be underestimating the seismic loads. So again, use the nominal unreduced properties for calculating the building periods. Now we'll calculate the notional loads. We'll apply notional loads in each direction at each elevated level. We'll specify the AISC standard tolerances, so we'll use 0.002 times the gravity loads. The notional lateral load for dead load is 0.002 times the dead and superimposed dead loads equals 5 kips at each level. The notional lateral load for the live load is 0.002 times the live load equals 4.5 kips at each floor, and the notional lateral load for the roof live load is 0.002 times the roof live load equals 1.4 kips. Next, we'll mesh the columns and define our stiffness reduction method in tau B factor. These screens are from SAP 2000. On the left screen, we selected auto meshing of the frame elements into 4 segments. On the right screen, near the middle, we selected stiffness reduction and using tau B variable, which means that SAP will calculate tau B for each element. The LRFD load combinations are shown here. In this case, we added the notional loads to the gravity load cases only. We'll need to confirm that later when we compare second order to first order drifts. Once again, the notional lateral load factors are consistent with the gravity load factors, and the notional loads are applied in both positive and negative x and y directions. In this case, we did not include the notional loads with wind or seismic loads. We'll need to confirm that assumption later when we check the second order to first order drift ratio. For simplicity of this example, we did not include any torsional wind or seismic cases. Torsional cases should also be included. Also, when we did not include any diagonal lateral cases for this example. In this case, the lateral systems in the x and y directions are completely independent and uncoupled, so diagonal lateral cases are not required. However, if you have a lateral system in the x and y directions that share common columns, then the notional loads nx and ny should also be applied simultaneously with appropriate directional correlation, just like other lateral loads. For the strength design analysis, we'll perform a second order elastic analysis that includes both P big delta and P little delta effects using reduced member properties. For the axial stiffness, we use 0.8 EA. For the flexural stiffness, we use 0.8 tau B EI. We'll start by assuming tau B equals 1, then we'll need to check that assumption later after the members are designed. We made our first pass for strength design using the reduced stiffness. Now we'll check serviceability with the strength-controlled member sizes. Remember, for the serviceability checks, we use the nominal unreduced member properties. So we toggle the stiffness reduction off in our 3D model, so the full stiffness is used, and then rerun the second order elastic analysis, still including both P big delta and P little delta effects. Here are the brace frame drifts and story drifts for a 10-year wind. Again, these are the unreduced stiffness properties. For brace frames, the drifts are well within the desired limits. Here are the moment frame drifts and story drifts for a 10-year wind. Again, these are with the unreduced stiffness properties. The lower four stories have more drift than our target of H over 400 for the 10-year wind. So we'll need to stiffen the lower level moment frames. We stiffen some of the lower level columns and beams to achieve the target drifts and optimize the frame for wind drift. The final member sizes are shown here. Here are the moment frame drifts for the optimized frame. Again, these are with unreduced stiffness properties. The column on the right shows the drift index for each level. We achieved the target drifts for all stories after stiffening the lower levels. Now we'll check seismic drifts. From ASC 7, the allowable seismic story drift is 0.02 times the story height, which equals 3-inch maximum allowable story drift. The maximum seismic story drift for our frame was 0.79 inches at level 9. Again, that is the drift determined using the nominal unreduced stiffness. And also that's the elastic drift, so we need to multiply by the C sub D factor of 3 to get an inelastic drift of 2.37. That's less than the 3-inch limit, so the seismic drift is okay. Now that we've stiffened the moment frames to get the wind drifts within the desired limits, we need to do a final check on the member designs for strength. So now we reduce the stiffness again in order to perform a second order elastic analysis, including P big delta and P little delta using the reduced member properties. For the axial stiffness, we use 0.8 EA. For the flexural stiffness, 0.8 tau B EI. We'll start by assuming tau B equals 1, then we'll check that assumption later. We'll run through the final strength check. Here are the sizes we ended up with after optimizing the frames for drift. Now we'll check them for strength. Tabulated here are the second order to first order drift ratios. The maximum second order effect is 1.49 based on nominal unreduced properties, which is less than 1.5, so our analysis is okay using the notional lateral loads with the gravity loads only. If the ratio had been larger than 1.5, then the notional loads would be required to be added to the load combinations with wind and seismic also. That being said, for a moment frame like this, I usually do add the notional lateral loads to all the load combinations, even though it's not required by the specification, especially when the second order effects are so close to the cutoff. Now we'll look at add some strength calculations, and we'll compare the direct analysis method with the effective length method design. Our analysis showed that the second order to first order drift ratio was less than 5, so the effective length method can be used in this case. Note, however, that it was very close to the cutoff, so if this frame was just slightly more flexible, the effective length method would not be permitted. For the effective length method, we need to rerun our analysis with the final member sizes, but now using the nominal unreduced stiffness. Notional lateral loads are already applied to all the gravity-only combinations in our model. We'll leave those exactly as we had them for the direct analysis method, since the notional lateral loads are also required for the effective length method. Recall the difference between the effective length method and the direct analysis method. Both methods have notional lateral loads applied in the gravity combinations, and both methods employ a second-order analysis, but the effective length method uses the nominal unreduced properties, while the direct analysis method uses the reduced stiffness. As you can see in the graphs here, the effective length method on the left uses a reduced compression capacity by applying the K factor to increase the column effective length, while the direct analysis method on the right uses a higher compression capacity based on the actual column length. Also, the effective length method has a lower moment demand, while the direct analysis method has a higher moment demand that more closely approximates the actual frame response. Let's compare results for the brace frames first. We'll look at the brace frame from the 5th to 6th levels enlarged here. Column 1 on the left, column 2 on the right, beam 1 is the lower beam 2 is the upper beam, brace 1 on the left, and brace 2 on the right. Here are the member forces for this section of brace frame for the direct analysis method in the top and the effective length method in the bottom for load combinations 15 and 16. Note that the direct analysis member forces are typically slightly higher than the effective length method forces. For the direct analysis method, K is always equal to 1. For the effective length method, since this is a brace frame, K is also equal to 1 for these members using the effective length method. So in this case, with the brace frame, the forces are only slightly higher for the direct analysis method, K equals 1 for both methods, and we end up with the same member designs for each. Now let's look at the moment frame. Remember that we stiffen the columns and beams at the lower levels to control drift, so we'll look at the moment frame members higher up in the building that were controlled by strength. We'll look at some moment frame members at level 6. The column below level 6 is column 3, and the column above is column 4. The beam to the left is beam 3, and the beam to the right is beam 4. Here are the member forces for this section of moment frame for the direct analysis method in the top table, and the effective length method in the bottom table for load combinations 13 and 14. Note that the moment frame axial loads in this case are the same for both analysis methods. However, note that the direct analysis beam moments are higher than the effective length method beam moments. Also, the direct analysis column moments are higher than the effective length column moments. This makes sense since the direct analysis method uses a reduced frame stiffness, it has more second order effects. For the direct analysis method, K is always equal to 1. For the effective length method, however, we need to calculate the K factor. So we calculate G top and G bottom based on the beam and column EI over L summations for each joint and use the side sway uninhibited alignment chart to determine K equals 1.4. This K is consistent with what most software packages will calculate for you when using the effective length method. However, we're not done with K yet. Remember, we only have 2 moment frames in the east-west direction, and we have a lot of leaning gravity columns that are stabilized by those moment frames. So we have to adjust the K factors to account for the effect of those leaning columns. The K equals 1.4 that we just calculated needs to be increased to account for the destabilizing effect of those other gravity columns. This is an often overlooked part of the effective length method and something I see missed a lot. There are a lot of assumptions that go into K factors, and many structures don't conform to those assumptions, and thus the K factors need to be adjusted. The IASC specification commentary has some good discussion on this and also provides some methods for adjusting the K factors for different situations, including adjustments for the effect of leaning columns. So here we're adjusting the K factor of 1.4 that we previously calculated. We're using the story buckling method approach found in the AISC commentary. When accounting for the leaning columns, the K factor is now 2.52 instead of 1.4. Therefore, you can see that the leaning columns have a significant effect on the capacity of the moment frame. Software packages I use give the first K, 1.4, but don't automatically adjust for the leaning column effect. So unless you manually adjust the K factors, the design would be unconservative. This is one of the big advantages of the direct analysis method, no K factors. K is always equal to 1, so you don't need to worry about adjusting the K factors. And for many structures, it can be difficult and tedious to determine the appropriate K factors. Okay, now we're finally ready to compare the direct analysis method design with the effective length method design. On the left are the calculations for column C3 using the effective length method. On the right is the direct analysis method. Let's start first with the effective length method on the left. The required moment is 5,397 kip inches and the axial load demand is 355 kips. We'll try the W14 by 99 column from our analysis. That column has a moment capacity, phi(mn), equal to 7,752 kip inches using table 3.2 or the equations in chapter F. Next, we calculate the column axial capacity. For the x direction in the plane of the moment frame, k equals 2.52, which is the modified k after adjusting for the leaning columns. So k over rx is equal to 2.52 times 150 divided by 6.17 equals 61.26. For the y direction, k equals 1 since that direction is braced by the brace frames. KL over ry is equal to 40.43. KL over rx is larger than KL over ry, so the major axis controls the compression capacity. The column compression capacity phi(pn) is 995 kips using the equations in chapter E. Now we plug in the interaction equation H1-1a and find that we have an interaction ratio of 0.98, so it works for strength. Now let's look at the direct analysis method on the right. The required moment is 5,831 kip inches, which is higher than the 5,397 kip inch moment we had for the effective length method. The axial demand is 355 kips, which is the same as it was for the effective length method. We'll try the W14 by 99 column again from our analysis with the moment capacity of phi(mn) equals 7,752 kip inches, the same as before. Again, this is using the nominal section property for that calculation. Next, we calculate the column axial capacity. For the direct analysis method, k is always equal to 1. So for both directions, the column effective length is the same as the actual column length. Since k equals 1 in both directions, the minor axis of the column now controls the column capacity, and pn is 1,162 kips. Again, this is using the full section properties. Note that this capacity is considerably higher than what we had calculated using the effective length method due to the differences in k. Now we plug into the interaction equation H1-1a again, but now the components of the interaction equation are different. The axial portion of the interaction equation has a lower DCR ratio than the effective length method, while the moment portion of the equation has a higher DCR ratio than the effective length method. The net result here in the end is almost the same, however with a total DCR of 0.97 versus the effective length method of 0.98. So we arrived at the solution in very different ways, but in the end we have the same design. However, the direct analysis method is superior because it's closer to the actual structural behavior, includes the right beam and column moments, and you don't need to worry about calculating and adjusting K factors, which are often misapplied. The direct analysis method isn't limited to just brace frame and moment frame designs. It can also be used for long span truss bracing systems. This is KFC Yum Center, a 22,000 seat arena in Louisville, Kentucky. We'll use this as an example of applying the direct analysis method to truss bracing. The roof and long span trusses were shaped to resemble a Cardinals wing for the Louisville Cardinals basketball team. The roof span is a little over 400 feet by 400 feet with 40-foot deep trusses. 4 vertically curved one-way trusses, highlighted here in red, span over 400 feet and support shorter transverse trusses, as well as a ring grid, center-hung scoreboard, speaker clusters, and catwalks. Gravity stability and lateral load resistance is provided by horizontal trusses shown in red at the top chord of the vertical trusses. For design of the roof lateral system, notional loads are applied to the trusses and added to all load combinations, thus combining the lateral load demands and the stability demands together. This last example of the direct analysis method applied to a more complicated long span roof system. This is Marlins Park in Miami, Florida, with a retractable roof consisting of 3 independent roof panels spanning up to 566 feet. 3 movable roof panels ride on steel wheels and steel rails along track structures. The 3 individual roof panels can all move separately and independently. There are 2 lower roof panels and 1 upper panel. Each roof panel is supported by a system of one-way trusses spanning on a skew from rail to rail. Each lower panel in blue has 3 trusses spanning 530 feet. The upper panel in red has 6 trusses spanning 566 feet. The trusses are up to 45 deep at midspan. The roof panel bottom framing is shown on the left. Diagonals and struts interconnecting the vertical trusses form wide horizontal trusses to provide gravity stability and resistance to hurricane winds. All the lateral resistance is at this bottom framing. The roof panel top framing is shown on the right. Roof purlins span the girders and girders span between the roof trusses. In elevations, the trusses are curved vertically. Here the upper panel is parked over the lower panels. In order to avoid large thrust to the wheels and rails, we provided a release mechanism on the low track side on the left to allow the trusses to move left and right at the left end without building up large struts. This means that all the lateral loads in the left-right direction are resisted at the high track end on the right side. And this is a section looking in the transverse direction. In the lower diagram, all the gravity, stability, and lateral resistance is provided by the horizontal bracing trusses at the truss bottom chords and braces that extend up to the upper chords to brace the top chords. In the top diagram, the moment frames that stabilize the roof panels in the left-right direction are highlighted in blue. We use flexible moment frames in each end, as you can see highlighted in blue here. So if you were analyzing this system using the effective length method, good luck determining the right K-factors to use. We used the direct analysis method to analyze the roof panel stability and design the bracing and moment frame systems. First, we investigated the potential buckling shapes of each roof panel using eigenvalue buckling analyses. These buckling analyses provided both the buckled shape and the factor of safety against overall system buckling. The primary global buckling mode of the upper panel is shown here. We initially considered using a series of displaced starting geometries that mimicked the buckling shapes, but eventually decided that employing the notional load approach would be easier to implement. We developed a series of notional loads to mimic the buckling shapes and applied those notional loads to the roof panels. Then the notional lateral loads were added to all load combinations. Here are some of those notional loads applied to the roof panels. These were notional lateral loads applied as area loads directly to the top surface of the roof panels. The notional loads were tuned to mimic the buckling shapes we were analyzing and the amount of initial panel displacements we were targeting. These notional loads were added to all load combinations, including the lateral load combinations. And here's a photo of the upper roof panel during construction. In summary, the direct analysis method is a versatile stability analysis method that can be used for any type of structure. It's the primary stability analysis method, and it provides a very good representation of the actual behavior in the strength limit state. The steps for employing the direct analysis method are summarized here. First, accurately model the frame behavior, making sure to capture all destabilizing loads and effects. Factor the loads, even for allowable strength design. Consider initial imperfections, usually by the application of notional lateral loads. For the strength analysis, reduce all stiffness that contributes to stability. Perform a second-order elastic analysis that includes both P big delta and P little delta effects. Mesh compression elements into segments to capture the P little delta effects. And then use K equals 1 for all member design. And finally, use the nominal unreduced stiffness for serviceability checks, such as deflections, drift, building periods, and vibration. Okay, Christina, I think we have some time left for questions.
Okay, great. Thank you, Dave. Perfect timing. We have quite a few questions from the audience. And just as a reminder, if you have not yet sent in your question through the chat, you can still do so. Okay, so for our first question, I'm going to take us to slide 51, just so we have a visual aid. Can you explain in more detail how the ratio of the second order drift to the first order drift is calculated within your computer model? Are you running separate models to calculate this ratio?
Yes, excellent question. So what we do is run a first order analysis and look at the deflections that we get at each level, and then calculate our story drifts from the first order analysis. And then we run a second order analysis and do the same thing and compare the drifts from the first order to the second order. And I think in example 4 we showed a table. Let me see if I can find what slide that is. We showed a table of the drifts, and that's exactly how that was calculated, was looking at first order and then second order and then comparing the two. So 2 separate models.
Okay, great. Thank you. And while we're on this topic, should this ratio of second order to first order drift be checked for all load combinations?
It can be checked for all load combinations, but does not need to be checked for all load combinations. Generally, the load combination you want to check this with is with the load combinations that have the highest factored gravity loads. Generally, that's going to be the gravity loads with the notional loads, or the full gravity loads applied with some other lateral load. The important thing here is that the combination of the frame stiffness and the gravity loads is what destabilizes the frame. So we want to check that with the highest gravity loads.
Okay, great. Thank you. And our next question. If the analysis software does not automatically generate your notional loads, can the direct analysis method be used with the governing load combination only in order to reduce the number of times the notional loads are calculated and applied?
I wouldn't say could be used with the governing load combination only, because there's so many different load combinations to check. If we had a very heavy structure with fairly light lateral loads, then I would be concerned if we didn't include notional loads with the gravity combinations. I think there's a couple different methods. One is to just manually apply all those loads. Another is to find out what your typical ratio would be and then adjust your load factors on those other lateral load combinations to factor them up accordingly. So those are two different methods, but the notional load should be included.
Okay, and then in the first order and the second order drift models, do you still need to apply the notional loads?
In the first order and second order drift, when we're checking, I assume the question is pertaining to checking drift for wind drifts and seismic drifts, as opposed to whether or not we need to include the notional loads, or whether or not we can use the effective length method. In those cases, you would not need to include the notional load to check the wind drift or to check the seismic drift.
Okay, thank you. The next question. The industry that I work in still uses ASD, the 9th edition specification. We're currently discussing changes to include P delta. Can you clarify how this will not create a more conservative design?
For a flexible system, the P delta effects will definitely increase the demands on the structure. Even in the old green book, if that's what you're using, the 9th edition, stability is still required to be considered. And even back then, we were running P delta analyses on most of our buildings. So it will result potentially in more conservative sizes if you have flexible frames. If your frame is fairly stiff already, then the secondary effects will be minimal, and you may not have any increases in demands or very low increases in demands. So it really depends on your structure. If you have a flexible structure, there will be increased demands going from second order to first order. If you have a stiff system, then that effect is very, very small.
Okay, thank you. Next question. Would it be overly conservative to always use the 0.003 alpha y sub I to avoid calculating tau sub b?
Good question. I don't think it would be overly conservative. Certainly it's not required. When you look at the 0.003 y sub I for a typical structure, at least one that I'm typically used to working with, compared to the lateral loads that are applied, say, for wind or seismic, they're usually fairly small compared to those wind or seismic loads. So for a structure like that, then no, I don't think it's overly conservative to apply the 0.003 instead of the 0.002. On all the examples I did here, I applied the 0.002 just because that's the approach allowed by AISC and wanted to demonstrate that. But it certainly is a simplification to put 0.003 for all of those, and then you don't need to go through the tau b calculations.
Okay, thank you. The next question, I think this is referring to slide 132. For this long span roof truss, the notional load is applied at the top chord level only. Why is that?
We applied the notional loads at the level or at the area that we were stabilizing the trusses with, and the top chords are the ones that are in compression. That's why we applied at the top chord only. I guess you could consider applying the notional loads at all the different locations loads are applied. That would be appropriate as well and could be done, but we just simplified it by applying all the notional loads at the top, which we felt would be conservative.
Okay, thank you. The next question, back to notional loads. How does applying a notional load of 0.002 of the gravity load relate to an h/500 displacement when we apply the notional load without regard to the frame or column stiffness? Why don't we just force a displacement of h/500 in the model?
You certainly, well, first of all, if you just take a simple column and apply the 0.002, that represents the forces that build up in the system from a h/500 displacement. And it certainly is optional to apply starting displacements instead of notional loads, and that's allowed by the specification and appropriate as well. We found it typically easier to apply the notional loads than to apply various sets of starting geometries. For instance, in the frames I showed, you would need to look at displacements in each direction combined with other loads, say lateral loads in each direction as well. So typically it's easier, at least in the software that we use, to use the notional loads instead, but certainly applying displacements is an option.
Okay, thank you.
In fact, we considered applying displacements in the Marlin's roof I showed you and trying to come up with displacements for the buckled shape and apply those, but again, we found it easier to apply notional loads that mimicked those shapes.
Okay, thank you. The next question. Since k equals 1 in the direct analysis method, it seems like the direct analysis method does not consider the restraints at the end of the members. Is this an accurate interpretation of the behavior?
No, the direct analysis method is considering the restraints. Remember, we're doing a second order analysis that considers both P big delta and P little delta effects using the model that represents our actual structural behavior. And we're softening the stiffness to represent what happens at the limit state with distributed plasticity. So I think the direct analysis method is probably the best method we have of accurately representing the actual behavior of our system at the strength limit state.
Okay, thank you. It looks like we have time for one more question. It looks like we do have quite a few questions that weren't answered, so we'll have to answer those after the webinar and respond by email. I'll take one more question. When designing the steel structure using the direct analysis method, what forces do you use for the base plate design and foundations? Do you use the notional loads?
That's a great question. So for the moments that you get out of your analysis are what you should be using for designing your base plates and anchor rods and foundations. The notional loads are really fictitious loads that we're applying to create that displacement. So the moments that result are valid. The shears, however, if you wanted to, you could subtract out the notional shears that you added into your system. You could subtract them out. Again, those are fictitious loads. And if you, say, take a simple column model and just displace it by the 0.002 or the h/500 and see the results there and then compare that to a notional load, you'll find that you can subtract that notional load out at the base of your column and end up with the same results. So it's usually a small load, so in our practice we typically just include it in there, but you don't have to. But again, that applies for the shears only. For the moments, you need to design for those moments.
All right, thank you, Dave. Again, if we didn't answer your question today, we will get back to you by email with a response.